In the name of God, good morning, ladies and gentlemen. I'd like to welcome on behalf of the University of Kashan our guests, our French dignitaries, to this workshop on meteorites and micrometeorites today, and welcome you. I'm sure you must be feeling very tired. You've just arrived 4 o'clock in the morning. Welcome to Kashan. I hope you'll have a pleasant stay. For the audience, as you have already known, we've got 4 guests. May I say Dr. Gounelle, correct? Professor Gounelle, Doctor, because I haven't got the titles here, so please, I'll just mention the names. Matthieu Gounelle, Pierre Rochette, Mr. Pourkhorsandi, and Jérôme, forgive me for the bad pronunciation, Gattacceca, correct? Please tell me. Gattacceca. Thank you. I'm sorry. Anyway, just let me explain to you about the Kashan University. Kashan is a very old town in Iran, with about 7,000 years history, recorded history, actually. First written about it, about Sialk, by a French archaeologist. And University of Kashan is nearly 40 years old. We have got a full range of all courses in engineering, in mathematics, in sciences, and several faculties, at least 7, 8 Center of Excellence for Research and Development centers in different fields, from nanotechnology, which is one of the best in Iran, it is the best in Iran, to water, to energy, different fields. We have research centers for that. About 8,000 students with a very good record on research and activities. For the last 20 years, we have always maintained a per capita research publications amongst the top 5 universities in Iran. Nearly 400 university lecturers, a good deal of interest in archaeology, in mining and mineral engineering, where there's a good deal of interest in what you're doing, and some students and researchers are very much interested to know about you, and hopefully there would be scope for cooperations. We know that you're here for a special trip later on. We hope, actually, I would like to make it very short and brief. Yeah, there's plenty to say about the university here. There is like every other university, to be honest. It's a very good university, and we like it. That's all I can say. But we hope and encourage all students and friends to be able, especially in this time and momentum which has started between our countries, cooperation internationally, we hope to be able to have a good deal of scientific cooperation established here and from now on. And we believe our greatest assets are our students. Although I'm a lecturer, but I still believe our greatest assets is our students in the whole of Iran. And there's plenty to do, plenty to learn, and plenty to love. God bless and thank you very much. May I invite our first guest, Sir Matthieu Gounelle, to commence his lecture. Please. لطفاً تشریف بفرمایید.
Hello. Thank you very much for inviting us. It's a great pleasure to be here in Iran and Kashan. And I will try to give a brief introduction to meteorites and what they serve us for to understand the early solar system formation and evolution. So, as you know, one of the most important discoveries in astronomy of the last 30 years, maybe of the last 50 years, is the discovery of exoplanets, meaning planets around stars other than ours. And so it means that planetary formation is probably very common. We estimate that probably one star out of two makes planets when it forms. So the goal of how chemistry, given the importance of planet formation and star formation in the galaxy and in the universe, is to understand the history of our own solar system, so the mechanisms which led to the formation of the Sun and the planets, but also to put it in the context, in the more general context of star and planet formation. So we have, in a way, two subjects of study. One, which is our solar system, which formed a very long time ago, but very close. We are part of it now. So it is a small spatial scale. And our second object of study is the formation of other solar systems now. So it's happening now, but this is very far in distance. But we try to combine both informations we can obtain from our solar system now and from astronomical observations of other solar systems to try to understand general mechanisms which lead to the formation of stars and planets. And there is one very important question we try to answer to, which is, did we need some special conditions to make our Sun and our planet, or is it a banal star and a banal solar system? So meteorites are very important in that respect because they are leftovers of the early solar system. I will come back to that later, but as you know, most terrestrial rocks are very young compared to the age of the solar system, so they have lost any record of what happened at the very beginning. And this is not the case of meteorites, which are our record of these early processes. And now we have a very large collection of meteorites in the world, amounting almost to 47,000 samples. Among these 47,000 meteorites, roughly 1,000, this is an important number to remember, have been seen falling. So which means that someone was there, or many people were there to see the meteorite enter the atmosphere, make a meteor, and then to see the stones drop. And this is relatively important to have these objects because they are fresher, they've not been disturbed by terrestrial residents. So whenever we have the choice, we prefer to work on these falls rather than on meteorites which are found in deserts. So this is what Pierre Rochette will talk about. 45,000 of meteorites have been found in deserts, most of them in Antarctica, and a significant fraction in hot deserts. The first question we want to address, in a way, when one works on meteorites, is where do they come from? And so, meteorites are fragments of solid bodies of the solar system, which are generated by collisions in the solar system, and these collisions generate pieces of rocks which travel sometime up to hundreds of millions of years in the solar system until they fall onto Earth. Typical travel time, if any, in the solar system after a collision between two bodies of a fragment may be of 10, 20 million years. So, from the orbits of meteorites, we know that most of them come from the asteroid belt. So, as you know, asteroids are small bodies which are located in the solar system between the orbit of Jupiter, between the orbit of Mars and the orbit of Jupiter. There are many of them, millions of them, larger than 10 meters. And for a handful of meteorites, maybe 10 or 15, we have been able to calculate the orbit using triangulation observations, either by chance or using dedicated camera networks. And these orbits show that most meteorites originate from this so-called asteroid belt. We have also some spectroscopic evidence which help us make the link between certain asteroids and certain meteorites. So in this plot, what you see is the amount of light reflected by a body as a function of the wavelength, so it's a spectrum. And you can see that in some cases the spectrum of some asteroids matches very well the spectrum of some meteorites. So here on the right, for example, you can see the spectrum of the asteroid 6 Heavy matches very well the spectrum in infrared and visible light of a chondrite. So using this orbital and spectroscopic evidence, we know that most meteorites come from asteroids. And here you have a few pictures of these asteroids, which have been the target of a diversity of space missions over the last 20 years. So these pictures, one needs to realize how impressive they are, because you can see now the details, craters, boulders at the surface of asteroids, cracks, and many geological features. So thanks to space age and space exploration, we have entered an era where asteroids are no longer point sources in telescopes, but real geological bodies that you can study. And obviously, meteorites are sampled from these bodies and are a way to study the geology of these asteroids. For asteroids, size matters very much, because whenever an asteroid or any planetary body is too big, it is difficult for it to cool down, right? Because you cool by your surface, and the larger you are, and the smaller is your surface relative to your volume. So the larger you are, the bigger you are, the higher your temperature goes. And eventually, if your temperature goes a lot higher, very high, a body can melt and differentiate. So this is a plot which shows you that the temperature of an asteroid as a function of time, and you can see that the larger the asteroid is, the higher the central temperature reached by the asteroid is. So large asteroids, maybe the ones larger than 100 kilometers, have reached temperature high enough to melt and to differentiate, as the Earth, for example, did, which is a very big body. The consequence of that is also that small asteroids have not melted. So if they have not melted, they are still very primitive. They have not changed since the early solar system, and this is why they can help us decipher all the physical processes which took place in the early solar system. So if most meteorites are from asteroids, it seems that a few meteorites, very rare meteorites, come from comets. So this is a work we've been doing a few years ago now. Orgueil is a very special meteorite whose chemical composition, I'll come back to that in a minute, is almost identical to that of the Sun, at least for all elements except for hydrogen and helium. But for all metals, its composition is similar to that of the Sun. So it's a very important meteorite. And it fell in 1864 in France. And we have a lot of very good papers describing the fall and describing the trajectory of the meteor provoked by the atmospheric entry of the meteorite relative to the constellations. And using these observations, we could reconstruct the orbit of the Orgueil meteorite. And what we showed is that the orbit of the Orgueil meteorite extended beyond the orbit of Jupiter, meaning extending into cometary regions. So probably Orgueil and the other 4 meteorites, which belong to the same class, has a cometary origin. This link between meteorites and comets is especially exciting at the present time, because, as you probably know, in last August, an European spacecraft called Rosetta reached a cometary nucleus. So Rosetta, which was launched in January 2004, more than 10 years ago, after 10 years traveling in space, reached the comet Churyumov-Gerasimenko. And what you see on the left is a very impressive closer picture of that comet, whose diameter is roughly 6 kilometers. And in November, so very soon, in 3 weeks, I think it is planned around November the 13th, if I'm not wrong, a small part will be detached from the spacecraft and land onto the comet. So this comet is especially interesting because it has a very weird shape, which looks a bit like a ball. So this is a 3D animation representing the comet shape from the data from the spacecraft. And you can see it's a very complex physical structure, probably due to the fact that 2 independent bodies have merged together, or that possibly a big body was broken and then reaccreted. After a lot of very complicated discussion, the landing sites have been chosen. So this will be there, that the Philae will try to land in November. As you see, it's technically very difficult because this is not an easy terrain, and obviously it is so far away from the Earth that everything will be automatic. So why is it important that connection between meteorites and comets? Why is it an important area of research to understand the fraction of meteorites which come from comets and what are their properties? Because in the solar system you have one frontier now, which is given by Jupiter. So beyond Jupiter, in a way, it is the outer solar system. It is a cold region, and probably all the bodies which accreted beyond, further away than Jupiter's orbit in the early solar system, accreted ice, right? Not only solids, and therefore have very different properties. And so this is what we like to study in the lab when we have cometary meteorites. Another set of very important meteorites are lunar meteorites, which we have roughly 180. You see one on the right, which is kept at the Natural History Museum in Paris. And these meteorites are very complementary from the Apollo or Luna samples brought back in the 1970s because they come from different parts of the moon. So that's why they are so important to understand the evolution of the moon. And we have also roughly 130 meteorites coming from Mars. And for Mars, we know they come from Mars because some of these meteorites contain very small gas bubbles which have been trapped when the meteorite left the surface of Mars. And the composition of these bubbles is exactly identical to the composition of the atmosphere of Mars, which was measured by the Viking spacecraft in 1976. So we know for sure that these meteorites come from Mars. And studying these meteorites is a unique way because we have no other samples from the planet Mars, and I doubt we will have in any near future. So these samples, these meteorites, are a unique way to study the geology of Mars. So a little diagram to summarize the different classes of meteorites. So meteorite study is a natural history study, so you can spend a lot of time doing classification. It's not that interesting. But it's important to realize that you have three main kinds of meteorites, which are the stones, the iron meteorites, and a mixture of the two, mixture of stones and iron. But most importantly, you have the meteorites which are called primitive meteorites, coming from these asteroids and comets which are small enough not to have melted in the early solar system. And you have differentiated meteorites which come either from the interior of differentiated bodies, this is the case of iron meteorites, or from the surface of differentiated bodies like Martian or lunar meteorites. So this is a big boundary in meteorites world, the boundary between primitive and differentiated meteorites. So primitive meteorites are called chondrites, and they represent roughly 85% of the meteorites fall. And you have three main types of them: carbonous chondrites, ordinary chondrites, and enstadite chondrites. So I will talk mainly about chondrites because chondrites are record the first million years of the nascent solar system. So they help us understand in what context the sun was born. So you know that stars are born in giant molecular clouds. Stars very rarely are born in isolation. They always are born in groups. And a very important line of research on meteorites is to understand how the sun was born together with other stars. How many stars were born together with the sun? How did they interact one with the other? Another very important line of research is to understand what happened in the so-called protoplanetary disk. So again, when a star is born, it collapses for a relatively large and extended amount of matter, which is called a dense core, which collapses gravitationally. And at the end of that collapse, you have a star, a protostar, surrounded by a disk. This is due to the conservation of angular momentum. So this is a universal process. Every star comes that way. So you have a protostar and a disk. And this is within that disk that the solids, little by little, agglomerate until they make planets. So this is key to understand what happened in that disk, the time scales, the physical processes. And this is what meteorites, in connection with astronomical observation, tells us. So on the right, it's a real observation of a protoplanetary disk, which you see, this is a thin black line between the two lobes. Okay, the two lobes are reflection light from the disk. And you can see a very interesting feature of these disks, which are these collimated jets, extending over hundreds of astronomical units. So, one of the most important properties of chondrites is that they have a chemical composition very close to that of the Sun. And this is especially the case of the organic meteorite, which I mentioned before. So this plot shows, it is a log-log plot. normalized to the composition of hydrogen, and it shows the composition of the Pourkhorsandi meteorite compared to that of the solar photosphere. And you see that for all elements, except for hydrogen, helium, and a few other ones, such as carbon and nitrogen, the composition of the Sun is identical to that of the Pourkhorsandi photosphere, to the Pourkhorsandi meteorite. So this is quite amazing because you have a stone, which you have in the laboratory, which you can handle in your hand, in a way, because you should not do that. It's a very friable stone, very precious, which weighs 40 kilograms, and we're able to compare its chemical composition to that of a giant mass of hot gas, the Sun, and it matches of our orders of magnitude. This chemical match concerns trace elements, such as lutetium or beryllium, but also major elements such as magnesium, iron, or silicium. So this is something very impressive, which tells you in a way that rocks like Pourkhorsandi, chondrites, are building blocks of the solar system. They are the solid leftovers of all the gas and the dust from which our solar system was made. Now, if we look at the inside of these chondrites, what are they made of in terms of components of petrography? So, on the top, you have an optical image of a chondrite. You can see made of these large white inclusions, which are inclusions rich in calcium and aluminium. They are called CAIs, calcium aluminium rich inclusions. They represent roughly a few percent of the rock, and they are very important objects to which I will turn into an instant. They are probably the oldest, the first formed solid in the solar system. Most of the rock is made of these little spheres, which you see on the right, which are called chondrules, which are rich in magnesium and iron. So these chondrules make maybe 80% of the rock. You can also find some isolated grain of metals, like iron nickel metal, which is very specific of meteorites, because you know that on Earth you don't have, you never or very, very rarely find metals within rocks. And all of this is cemented by a small grain matrix. So CAIs are also called refractory inclusions. As I said, they are objects of a characteristic size of 1 millimeter, made of minerals rich in calcium and aluminium, formed at very high temperature, probably close to 1800 K. And we believe that they were formed very, very close to the Sun, maybe within a few 0.1 astronomical unit from the Sun, where the disk was very hot. And after they were formed close to the Sun, we believe they were transported outwards until the terrestrial region or the asteroid region by these jets. We saw before that this disk, so here on the right you have a sketch of an accretion disk, and you can see the protosun and the Sun at the center, the disk in red with its central part where most of the processing happens in green, and these disks usually have collimated outflows, which are due to the complex magnetic interaction between the star and the disk. And these outflows are observed. On the left, you have real astronomical images of outflows in disks observed now around protostars. And we believe that these jets could pick up solids like CIs from nearby the Sun to deliver them everywhere in the solar system. Chondrules are different objects that are maybe 100 up to 1 millimeter in size. They are very rich in typical olivine and pyroxene, very mineral, very common, which you find on Earth too. Magnesium and iron-rich pyroxene, and they also contain glass and metal. They are believed to have been made also at a relatively high temperature, but during a transient heavens, so heat up very quickly and cool very quickly. And so the most satisfying model for making controls are shock waves in the protoplanetary disk. But this is still a very active area of research, and this shock wave model may not be the right one. So, as I said, all these components are cemented together by a matrix, which is a very fine-grained component, very difficult to observe. You can observe it only by transmission electron microscopy. This is this is an image of transmission electron microscopy shown on the left, and it is made again of pyroxene, olivine, metal. But you have two very interesting components in the matrix. The first one are very small grains, which are called presolar grains, which are most of them silicon carbide, a few of them are graphite or diamonds. And these objects, I will come back to it in 1 second, are believed to be to be solids which have survived to any physical processes in our solar system, and therefore which have been made in stars anterior to ours. And also, the matrix preserves a lot of organics. I will come back to that in an instant. So, presolar grains are very exciting objects because they have an isotopic composition which is totally different from that of the Earth. So here you have a plot showing the isotopic composition in nitrogen and carbon of maybe 1,000 presolar grains. And you see the solar system composition in the intersection of the two lines. And any terrestrial sample or any bulk meteorite would plot at this interaction as a single point. So it means that these presolar grains are highly isotopically anomalous. They have isotopic composition which have nothing to do with that of the solar system. And so they are not very abundant, only a few hundred ppm in the most primitive meteorites. They are very small, maybe 100 nanometers in size, and they are believed to have formed in the atmosphere of stars which died million, maybe 100 million years before the formation of our solar system. So their study is very important because they help us to do two things. First, to understand nucleosynthesis within stars, because they condense in the atmosphere of stars, so that direct record of nucleon synthesis inside of a given star. And also they help us understand the chemical composition of the galaxy. So it's a very important area of study.
So, let me get your point. Is that just some inclusion in that meteorite or the total chemical composition?
No, it's very small inclusions of that size. Yeah, there is an image here. It's very small. It's like very rare, very small grains, which you obtain dissolving the meteorites in acids and keeping only a very small residue, which is acid resistant.
How do you know if you see a meteorite like that there could be an inclusion in the world which is prehistoric?
You cannot really know. Well, you know from stars that some meteorites are more likely to contain them because you can see that they have been less processed in the solar system. But then you need to do the experiment then to prove to discover these guys.
Does it mean that you get it just a chance, or how is it?
It's not by chance. Let's say that among the collection, all the meteorites we have, we know that a small fraction of these meteorites, maybe 1% or so, has a good chance to find to contain still these grains. In other meteorites, they have been destroyed because the meteorite was slightly heated or because water circulated. They've been destroyed. So very few meteorites preserve these very precious grains.
And is there any way to make an aging estimation of it? Or?
Some people are trying. It's a very good question. It's a very important issue. It's very difficult because they're very small. And so it's starting. Some results have been presented. So they found like ages like 10 million years before the solar system or something like that. So another component of the matrix is the organic matter. So in some meteorites, you can find up to 5% organic matter, which is trapped in the matrix. Most of it is just insoluble organic matter, kerogen-like if you want. But 30% of this organic matter is made of soluble components, among which amino acids and also sugars and nucleobases. Nucleobases which are make the structure of the DNA. So a very important line of research is to understand in what respect meteorites, especially carbonaceous chondrites, can have delivered organic matter and water onto the primitive Earth, and which made the basic for life to subsequently develop. So the last and obviously what meteorites tell us too is all this, the history in the disk of all this solid growth. Okay, so we start with gas and very small solids such as the pre-solar grains, and they go little by little, first making chondrule and sea ice object-likes, then making larger objects which are called planetesimals, which are, if you want, asteroids, then planetary embryos, and finally planets. And all this happened, well, at least the first 4 stages of growth happen in the protoplanetary disk. And what we want to do from meteorites is to have an idea of the time scales of this solid growth until planetary formation. So to do that, we use radioactive elements, and there are several kinds of radioactive elements. 2 are especially used to provide absolute ages, which are uranium-238 and uranium-235, and they are called long-lived radionuclides because their half-time is comparable to that of the age of the solar system. And using these radioactive elements, we can have absolute ages of objects. And now, over the last 5 years, many groups have been able to date CIs, and they all find this common age for CIs of 4, 5, 6, 7 million years. So CIs are very refractory objects, which we believe were formed in the disk very early, and we know how early it was, and this age defines the age of the solar system. So, solar system, CIs formed 4, 5, 6 million years ago, plus or minus 1 million years, and this is the age of the solar system.
So, what do you mean by solar system? Is that the age of the sun, or was it even before the collision of maybe 2 stars leading to the solar system?
No, we believe this is roughly the age of the sun. What we date is the age of CIs, of these inclusions within meteorites. This is the only thing we can do. Obviously, we cannot date the sun, or we can date it, but with very big uncertainty. And we believe, we're not absolutely sure, that this happened, these solid forms, just after the protostar, after the protosun was formed, within 1 million years of the sun formation. So we believe it's identical to the sun formation.
So you're sure this is not only any pre-solar?
No, we have good arguments to know that it's not pre-solar. And this has been studied in detail. It's most probably solar system objects. These CIs, these white objects here, were made in the solar system. And this age is the oldest one we ever measured. So we believe this is the age of the solar system. Another way to date objects is to use short-lived radionuclides. So these guys are slightly different. They are radioactive elements, but their half-life is a lot smaller, right, than the age of the solar system, which we just saw is 4.5 billion years old. So obviously they have now entirely decayed, right? So one example is aluminium-26, excuse me, which decays onto magnesium-26 with a half-life of 0.7 million years. So all the aluminum-26, which was present in the early solar system, has now decayed. So what we detect now is not aluminum-26, obviously, but is magnesium-26. Okay, excesses of magnesium-26. So the way it works is that one. You pick an object like CIs, which is made of different minerals, and you try to find minerals which have different aluminium to magnesium ratios. Okay, so you have aluminium-rich minerals on the right of the diagram, and aluminium-poor minerals on the left of the diagram. And for each of these minerals, you measure both the aluminium to magnesium ratio and the magnesium isotopic composition, which is on the y-axis. And you see that the horizontal dot line is the terrestrial composition, the normal composition. And you see that in CIs, so any terrestrial sample would plot in this dotted line at the bottom of the diagram. But in CIs, the minerals which have elevated aluminium to magnesium ratio have large excesses of magnesium-26. And we do interpret this excess of magnesium-26 to the decay of aluminium-26. So aluminium-26 is gone, but the inclusion has preserved the memory of its past presence thanks to the excess of magnesium-26. And not only can we demonstrate that aluminium-26 was there, but from that kind of diagram, which is called an isochron diagram, we can measure the concentration of aluminium-26, which was in the inclusion. And this concentration for CIs is 5 10 to the minus 5. So this was discovered in California in 1977 by Lee. So it was probably one of the most important discovery meteorites of the last 50 years. So using these short-lived radionuclides, you can do chronology. So you have not only aluminium-26, but you have also hafnium-182, which decays to tungsten-182 in 9 million years. And using different kinds of these short-lived radionuclides, you can date different families of objects depending on the half-lives of the short-lived radionuclides and on their chemical properties. Okay? For example, hafnium-tungsten is very powerful to date planetary differentiation, because hafnium is a lithophile element which goes into the mantle and the crust of planets, and tungsten goes into the core. So you use this chemical fractionation between these two elements to date this planetary differentiation process. And the age difference is calculated between two objects very easily using very simply the radioactive law. Okay, so if we saw that CIs had a concentration aluminium-26 to aluminium-27 of 5 10 to minus 5, any object which will have a lower concentration of aluminium-26 will be interpreted to be younger, and the difference in concentration will tell us the age difference using the decay radioactive law. So since the discovery of aluminium-26 in 1977, many measurements were made, and we know that most CIs were formed with the same initial ratio of roughly 5 10 to the minus 5. And chondrules, these objects which make the bulk of chondrites, so which are very important, have been also dated, and they have a lower aluminium-26 to aluminium-27 ratio, which is not shown here, unfortunately, on the diagram, but which is 1 10 to the minus 5. Okay, so it is a factor of 5 lower than the aluminium-26 concentration in CI. And using the decay law, you can show that it means that chondrules form roughly 1.5 million years after CIs form. Okay, so you have these two main components of chondrites, CIs which form first, at the very beginning of the solar system, and chondrules which form 1.5 million years later. So this helps you to date asteroid accretion, because this is a distribution of the ages of chondrules. So you can see this is the bottom x-axis is a concentration of element 26, and you can see a peak around 0.7 10 to the minus 5. CIs form with 5 10 to the minus 5, okay, on the left of the diagram. And if you transform that into age, just using the decay law, it means that most chondrules form 1.5 2 million years after CIs. And that all chondrules formation stopped maybe 4 million years after CI formation. So this gives you, in a way, an estimate of the time scale for accretion of asteroids. Okay, so all the asteroids probably, or all chondritic asteroids, form after chondrules were made, because asteroids are made of chondrules, so you need to first make chondrules and then form the asteroid. So they all form maybe 4 million years after the start of the solar system. And interestingly enough, you can connect that to disk observations. And on the right, you have images of disks in Orion. So these are disks around protostars. Okay. And on the left, this diagram shows the fraction of disks with a given age. And you can see that most disks have an age lower than 5 million years. Okay, so this is in agreement with our meteorites record. We show that probably after 4 or 5 million years, you did not make any more chondrules. Your disk was almost finished, and you started to make asteroids. And this is also what you observe with stars forming now. Another big success of dating is the dating of iron meteorites, which are the core of large differentiated asteroids. And this was a very strong surprise many years ago, or a few years ago, when people discovered, using the hafnium-tungsten system, that many iron meteorites form at the same time than CIs. So it means that we have also some bodies which form very early in the solar system and differentiated very early in the solar system. And the same hafnium-tungsten system was used to date the formation of the moon. So we believe that the moon was formed by an impact between the proto-Earth and another planetary embryo, roughly the size of Mars. And we can date that now, and we think it happened within 70 million years of solar system formation.
How sure are we that the moon is somehow related to the Earth?
Because they are very close in isotopic composition. So, for example, the oxygen isotopic composition of lunar samples is almost identical to that of the Earth. And there are other elements for which it is the case.
Any signatures from dating?
From?
Dating of, or aging of moon and the Earth, any data on that?
So it's complicated to directly date the moon formation using, for example, uranium dating, because there were very strong volcanic events on the moon 3.8 million years ago, which in a way erased any previous process. So the best way to date this impact is to use the hafnium-tungsten system, and this is shown to have happened 70 million years after the formation of the solar system itself. So if we want to summarize a very simple chronology, you would have, so this is a time in a log-log plot, log-log representation. It's not really a plot because you have only one horizontal axis. You have CIs forming at the very beginning of the solar system. Chondrules, which have an extended formation timescale for several million years. Then I've not had time to speak about metamorphism and hydrothermal alteration, which are geological processes which happen on early form asteroids. And also, we know now that some bodies differentiated very early, within also a few million years of the solar system. So all this has been deduced from all this dating exercise I mentioned before. And a very last point, these short-lived elements, like aluminium-26, their presence in the solar system is a big mystery by itself. Okay? Because, as you know, all elements which make the solar system, except for hydrogen and helium, they were all made by stars, which were belonging, which were living in the galaxy before our solar system, right? And synthesized carbon and oxygen and iron and all these elements were made by stars and then incorporated in our solar system. It is also the case of aluminium-26. But aluminium-26 decays very fast, okay? 1 million years. In a few million years, when you make, let's say you make a certain amount of aluminium-26, in a few million years it's gone. You have nothing left. It has all decayed. So it means that the star which made the aluminium-26, which was present in the solar system 4.5 billion years ago, exploded or lived, was very close to the solar system. And so this has been a big mystery for many years, which we might have solved recently. And so we have, we believe now that aluminium-26 was introduced in the solar system by a massive star. So what we believe now is that you had a very massive star whose wind contained aluminium-26, which was made in its interior, and contaminated a shell of dense gas, which was accumulated by the wind itself around the massive star. And we believe that the Sun and other stars were born in that aluminium-26 shell around that massive star. So this is also one of the power of this meteorite study, which it helps us to understand the astrophysical context of the Sun formation. So I will end here. And so, if there are a few things to remember, is that meteorites come, most of them from small bodies, but we have also a few planetary meteorites in a way, that they all record early solar system processes, which are very complex, which happen into the disk, and probably the disk phase lasted a few million years, maybe 5 million years. And using meteorites, not only do we have a chronology of the solar system first million years, but we can also understand the astrophysical context in which our Sun was born. And thank you very much for your attention.
Any question you may have?
First of all, I'm trying to your speech on a simple question of the meteorite. As you know, at a cosmological point of view, all of the matters in the cosmos or in the air, so they are meteorites, they are cosmological dust. But on other point of view, we must have a definition about classifying the meteorites stones, which they are meteorites or not. What's a specific signature to classifying them? I don't know, maybe the unique combination of matters which they have, or the age. Will you say what's the significance?
Well, to start with, as I showed, their chemical composition is very special. The chemical composition of the Sun is very close to that of meteorites, is very close to that of the Sun, and it's not the case of any terrestrial sample. Any terrestrial sample, if you compare it to the Sun photosphere, it will have nothing to do. So this is one way. Another way is to show that meteorites contain cosmogenic elements, radioactive elements which were synthesized during the travel in space between the asteroid and the Earth, because they were irradiated by galactic cosmic rays, and you make cosmogenic elements. So this is also a way to demonstrate that a stone comes from the outer atmosphere.
I was want to ask, is it true to say that all the matters in the cosmos or in the Earth, at least they are meteorites or not?
In a way, yes. It's not wrong to say let's be limited to our solar system, because each solar system has its own meteorites. But if you want, you can say that the Earth is a big meteorite. You could say that. I mean, the Earth was made from the accretion of many asteroids and planetary embryos, and you could say since the building blocks of the Earth are meteorites, you could, in a way, say that the Earth is a big meteorite, if you want.
Do we have unique meteorites from their combination of matters in the Earth, as they are not typical combination of the first matter?
All meteorites have a composition different from the Earth. Yes.
Thank you.
Please. Many thanks for your nice presentation. I've got a question about the chemical composition of the findings. Is it possible to predict the source, the component of the source material in the space from meteorites on the space on the Earth?
To predict before it falls.
To clear my question, for example, when something comes from the space to the Earth, there is atmosphere. Okay?
Right.
There is a different viscosity between the atmosphere and the space. And when the material approaches to the atmosphere, there is a viscous dissipation.
Right. Yes.
And the viscous dissipation changes the material, the source material, and maybe a chemical reaction occurs in the motion.
There is indeed a chemical reaction which happens, but which concerns only the very outer part of the meteorite, which is oxidized and burned, and it makes what we call a fusion crust around the meteorite. But the composition of this fusion crust is roughly the same as the meteorite. It's just a bit more oxidized and black. I have a picture. So all meteorites, when they are fresh, they have this fusion crust. Like this is what you see on the left here, for example. I don't know if I have another image. Probably Pierre and Jérôme will show you more of this fusion crust.
My second question is related to the how can you find the meteorites visually? For example, the archaeologists find some ancient things on the Earth that's like handmade things. How do you find them visually?
So I think Jérôme and Pierre will answer to that question more specifically, but mainly because of their color. The color of the meteorite is different if you go in the right place to the neighboring terrestrial stones. It is dark or rust-like, but they will speak about it.
If anybody would like to speak in Farsi, please go ahead, I'll translate. Because we have the Farsi, so I'll
Thank you. When I start to present when I thank you for the information, the conclusion study in meteorites family or similar to conclusions in economic geology for copper deposits, especially for fossil copper deposits. Or no, your instruments and equipment are similar or no?
I think probably the instruments are similar, but the nature of the inclusions is very different. But I'm not a geologist myself, so maybe my colleagues who are geologists can answer better to that question than, because I'm a physicist to start with.
Yes, good inclusions are studied in meteorites, especially in differentiated meteorites that have behave like magmatic rock and then have suffered hydrothermal aberration, etc. So we studied all these good inclusions to tell something about the fluids that were circulating in the, for example, on Mars. It's very important, those good inclusions. So yeah, they are studied.
But we talked about temperature of crashing, correction, and composition of the inclusion. Are you studying another variable in your study or no?
Yeah, one problem of also fluid inclusion in meteorites is that a lot of them are due to shock, because when a body in the solar system receives a shock, often there are veins of melted material with high pressure and high temperature, and so you get estimate of pressure and temperature using minerals in those veins, but also using fluid inclusion. But it can be from 2000 to 200 Celsius. It's very variable.
Thank you.
Thank you very much.
Thank you.
So it's okay, yes, the sound. So now that Matthieu has explained to you why it's important to study extraterrestrial matter, now let's get sample. So as he said, a lot of meteorite sample come from Antarctica, so I will develop this point. And so this is a picture I took 11 years ago in Antarctica in an expedition led by Italian party, and this was my teacher, Luigi Folco, who has gone a lot of time in Antarctica to collect meteorites. So I learned a lot from him, and I wanted to dedicate this talk to him.
Are you all in the picture?
I was taking the picture. You will see me in the other picture. So yeah, we need sample to measure all those fancy stuff that Matthieu showed. So one way to get sample is to wait and see. So if you see a bolide in the atmosphere, like this guy, or this one, eventually those bolides they fragment. And if you follow the trajectory, like this is a camera, automatic camera in Japan, or the other film was taken by a guy looking to a baseball match in USA. So he saw this. This is the light of the baseball. He saw this bolide that fragmented. And then you have to calculate the trajectory or estimate the trajectory and map it, and then look for the meteorite at the end of the trajectory. And this guy was seen here and fell in New York, and there was a big hole in this car.
So what's the time scale of the picture of the film?
It's like 30 seconds, 20 seconds, tens of seconds. Yes. The problem is you have only less than 10 falls that are recovered every year, so everybody gets excited after each fall. Sometimes so they fall in the field and you get a small crater and get the meteorite. This one was 8 kilo, I think. This one is very interesting. It was a big event, like I think 10 tons of material, but it exploded in the atmosphere, so a lot of small stones fell on ice, on lake that was frozen, so a lot of meteorites were collected on the ice. And sometimes there are big meteorites. This was in Peru. The crater is about 5 meters, and the meteorite is sitting in the water there, and they recovered it like it was 400 kilo. But we need more sample because, of course, there are more than 10 scientists working on meteorites in the world, and also we need to sample the whole variety of the solar system. For example, there is no lunar material that has ever seen to fall on Earth. So if you restrict to the fall meteorite collection, you miss a lot of type of meteorite. So the other way to get material is to go in museum. This is a piece of cicotalin in the Museum of Moscow with our PhD student from Moscow. She's now a researcher in Russia. And of course you have a lot of very nice rare material in museum that again they have been studied already by other scientists, so we like to find new material. So if you want to find new material, the expensive way is to go to space, and for example to get lunar material. This is from the Apollo program. Or if you have less money and you want more material also, because you cannot bring big samples from the space, you can go in desertic area. Desertic area, you find easily meteorites because they are not, they don't disappear in the soil with the weathering and burial. So they stay on the surface and you can collect them a lot of time after. So this is from Chile, again with a PhD student from Chile that we have trained. And this is from Antarctica, one meteorite we found. I like this picture because we found it while flying with the helicopter, and we saw it, and we asked the pilot to stop, and we collect the meteorite. It was fancy. So our team in Aix-en-Provence.
Could you tell just for saying that it must be new one, new info?
Oh no, we don't know when it fell. Maybe 100,000 years ago, or
because of the snow and melting and all that in the previous year. If it had fallen to the earth 300 years ago, it couldn't be seen just like that.
I will explain later how it works in Antarctica. So just to summarize our experience in Aix-en-Provence and also with our colleague in Paris, we've done for meteorite collection 3 missions in Antarctica, also micrometeorites, you will see. I've personally collected 150 meteorites in Antarctica. We did a lot of mission in Chile, in Atacama Desert, so we collect more meteorites in Chile than in Antarctica. We did also 2 missions in Tunisia, less effective than Chile. Also recently we went to Poland. We found only 1 meteorite, but it was a big one, iron meteorite. And this is me in Chile collecting a meteorite. So now let's concentrate on Antarctica. So Antarctica, the most part of Antarctica is the ice sheet. So it's a few kilometers of ice, and in a few spots you have mountains that spot out of the ice, and they are called nunataks. And the flow of ice, so this is the ice sheet from Antarctica. The flow of ice is disturbed by those nunataks, and so they want to flow from the center of the ice sheet to the ocean. And if they encounter this obstacle, the ice will come up. And in those zones there is a lot of wind, because you have always high pressure from the center of the ice sheet, and you have always wind blowing, very often a few hundred kilometers per hour. And so this wind just ablates the ice, sublimates the ice in those zone of uplift of the ice sheet. So the old ice disappears and carries the rock that is in the ice. So if a meteorite fell here, then was buried by the snow, then at this point it came out and pops out like mushroom. And so maybe the meteorite that you find here fell 1 million years ago, 100 kilometers or even 1,000 kilometers away. So it's a complex process. And so to find meteorites in Antarctica, we try to locate those zones. It's very specific zones near the mountains. Not everywhere you can find meteorites. So the area where I've been working is in this area here, along the Transantarctic mountain. Most of Antarctica is just ice sheet. You don't have mountain, but here you have these mountain chains with those nunataks that pops out of the ice sheet, and that are a good place to find meteorites. So this is the Italian base is here. So the Italian people were working in that area To the south, it's the US base and other bases, so most of the meteorites are found more in the central part of Antarctica. So when you go in those fields where the old ice come up, it's called the blue ice field. You get old ice that is ablated. There's no snow, just this old ice that comes out and piece of rock. So you see in this image a lot of pebbles of granite, and this rounded black pebble is a meteorite. So here it's very easy to spot because you see it's black and rounded, while the terrestrial rocks are angular and clear like a granite. But sometimes it's not so easy. I'm sorry, I prepared another version of the talk, but it's in another directory. So one question when we collect so much samples, hundreds, even thousands, after field work. First, in the field we want to be sure it's meteorites. We don't want to bring all the rocks that we see. And second, if we bring the normal way to characterize meteorites is to make thin section, microprobe. It takes days of work, and so we would like to have an easy way to say if different fragments are from the same meteorite. If we have 100 fragments, they are all from the same meteorite core. It's not necessary to make microprobe on every sample. So one way to solve this question is to study physical properties, and magnetic susceptibility is a very easy physical property to measure, and I will show you an example of this. So magnetic susceptibility is mostly linked to the amount of metal in the meteorite, but also it could be linked to the amount of magnetite and eventually pyrrhotite, the magnetic sulfide. The interesting thing is you can measure all sorts of samples, big samples, small samples, no problem of mass or size, and it's very rapid, few seconds per measurement, and you can measure even directly on the field, on the ice, or etc. So with years, we have assembled a database on more than 4,000 meteorites, and we have demonstrated that magnetic susceptibility provides a way to rapidly classify chondritic materials. So this is the example of the most common type of stony meteorites, ordinary chondrites. There are three types of ordinary chondrites called high, H, L, and LL, which means high, low, and very low in metal. So you expect that the magnetic susceptibility here in log unit will be the largest for H meteorite, intermediate for L meteorite, and low for LL. And you see that in those histograms that mostly if you measure like 5.2, you are sure it's H meteorite. Even eventually there's no need to do microprobe, etc. With a measurement that takes a few seconds, you can already say, well, it's H or L chondrite. So this is a summary of the average magnetic susceptibility of different type of chondritic material. So again, the three type of ordinary chondrite. You see the average susceptibility with the standard deviation. They are clearly distinct from LL, L, and H. And the other chondrites, they are very variable. You see it varies over nearly 3 orders of magnitude. There is one type of chondrite, the R Romuruti chondrite, that is very low in magnetic material. Then carbonaceous chondrite, they have variable amount of metal or magnetite. And then you have the unspatite chondrite and also the CH chondrite that are very rich in metal. So it's mostly here. If you had pure metal would be here. So if you measure magnetic susceptibility on a given meteorite. These are examples of meteorites you can find in museum that fell like L'Aigle. It's very famous. It fell in France 2,000 years ago about. And there are a lot of samples in different museums. And L'Aigle sample, whatever the mass is, you see it gives a fairly concentrated value of susceptibility, and so you can distinguish L'Aigle from Holbrook, for example, or from Jérôme. They have distinct values, but there are some anomalies. Like for example, this is from the Vatican collection. In Roma, they had a L'Aigle sample that was showing a very high susceptibility. And they had a Pourkhorsandi. Pourkhorsandi is from Poland. They had a Pourkhorsandi sample that shows a low susceptibility. So there was a problem. Are those meteorites heterogeneous in metal content? In fact, what we demonstrate with the curator of this museum is that through the time, these samples, they remain for 2 centuries in the collection. And they were passed from one guy to another. They look, they make exchange, and very probably they mixed up samples. So this sample is not from L'Aigle. We demonstrated this. It's probably from Pourkhorsandi. And so we found that it's a bit troubling, because in museum you have a certain number of samples that are not what is shown on the label of the museum. So every time you get a sample from a museum, even if it's written this is a L'Aigle sample, it's better to check that it has not been mixed up. So of course the metal it rusts with time. So you have weathering and the metal rusts, and the meteorite is less magnetic. So the magnetic susceptibility decreases with weathering. You can see it by comparing. So if you have H-chondrites, the histogram of magnetic susceptibility for fall here, if you look at Antarctic meteorites I've measured, the histogram is how do you say that? I'm sorry, I'm a bit tired. Is at lower susceptibility, and if you look at other finds, mostly from the Sahara, in fact, this database, they are even more weathered, you see. And there is a way to know when a meteorite fell on Earth. This is what is called terrestrial age, using carbon-46. And so there is a collection from Sahara where the age of fall on Earth has been measured. And I've measured also the magnetic susceptibility, and you see the magnetic susceptibility decrease with age. So it shows the amount of rusting is proportional to time on the Earth, which is what you expect.
What is the error of Kashan age estimation?
Yeah, it's a bit large. So let's say this sample is dated at 12,000 years, plus or minus 5 maybe. It's a big error bar, because there are a lot of assumptions on this method. I have no time to explain. I think Jérôme will explain this method later. So back to Antarctica. The first picture I showed you was among granitic rocks, so it was easy to spot the meteorites from the granite. But then we worked in an area where there was black schist and also basalt, and it was not so easy to spot the meteorites. So for example, you see, and meteorites are often small samples. You see, this is like a cigarette, so it's 6 centimeters. So if you see a black spot on the surface of the blue ice, and you see a lot, you see here, there were 3 of them. You want to know if it's a meteorite or not, if it's worth collecting it. So if we measured the magnetic susceptibility right on the ice, so this black rounded pebble gave a value of 0.036, and this one gave a value of 19. This one is full of metal, this is a terrestrial schist. And on the picture, they look exactly the same. Also, we want to collect every material. It's not only the big ones, also the small ones. And you see, in some places there is, it's a morainic area. You have grinded granite, so it's mostly a sand of granitic fragments. And you see a small black here or here. And with the eye or even with the lens, you don't know if it's a meteorite or not. This gave 001, this gave 2.86. So this one we collected, later we found it was really a meteorite, and this one we left it on the field, not losing our time. So this is how we work there, we camp. You need very special tents because you have to resist to very strong wind. Also you have to resist to the temperature. It was between -15, -20. And so you see near those granitic mountains that pops out of the ice, you get those blue ice fields, some snow also. And then you look for meteorites among those rocks that are at the surface of the blue ice, but you think probably there are also meteorites under this snow, because you see it's secondary snow drift that arise on the blue ice and that can cover meteorites. So what we tried was to use instruments to locate meteorites under the ice, and this is a magnetic gradiometer here. This material is mostly sold to military people to collect unexploded ordnance, but it's very useful for meteorites. So I show you the small movie, maybe with the sound. So you see it's the snow, and then I got a signal here. So it's very limited, a few centimeters, so it must be a small sample. Distance, even a few centimeters. So you see that there is a snow, and then below there are rocks, granitic rocks, and a small black rock that was a meteorite. So not big. But of course you can detect a small meteorite just 10-20 centimeter distance from your detector. If you get a big meteorite, you can detect it 3 meter, like the one in Poland that we found with those detectors. It was at 3 meter depth, but it was very big, 300 kilos. So, yeah, I'm sorry. It's an earlier version of the talk. I reorganized it, but the correct version is elsewhere. No problem. So now I will finish with micrometeorites, because there's not only meteorites. You have also small material, small extraterrestrial material that arrive on Earth, and in fact. The vast majority of the matter extraterrestrial matter that arrives on Earth is dust and sand fraction. The meteorites, they make a very small amount of this flux, so it's interesting to study also this micrometeorite flux. So this is a picture from sand that we collected in Antarctica, so mostly granitic sand, quartz grain, and then among those quartz grain, here the size is probably 0.5 millimeter. You see rounded grains, and if you get closer to it, you see it's very smooth and it has a strange shape, and you recognize it very easily by the eye. So this material was known since expedition on deep sea sediments. We calculate 1 grain like this These are pictures that were hand drawing from the microscope. There is about 1 per year per square meter that fell on Earth everywhere. So if you look carefully, you should find them. If they are not if it's easy to recognize. So of course, if you have a lot of pollution from volcanics, from human activity, you will have hard time to find it. But if you go to the deep sea, if you go to Antarctica, you can find them. And so they were found in those deep sea sediments with very low accumulation rate. And this is just to show the quality of the hand drawing from this date. This is an iron micrometeorite, and this is a SEM picture of one of the micrometeorites I've studied, very similar. And this is what is called barred olivine micrometeorite, and from this expedition, and SEM picture from our findings. This is from Egypt, I think, those 2 samples. So a lot of meteorites have been collected in Antarctica because it's very clean environment. You get only the snow and the dust, extraterrestrial dust that come, also some volcanic dust, etc., but we can recognize it. And so one way that was used to collect micrometeorites was to look in the water well from the South Pole base. So it's you see, this is 100-meter scale. So to get water in the South Pole, what they do is they made a drill and they heat the ice and pump the water. So after several decades of use of this system, there is a big hole in the ice, and with a layer of water because of the heating, and then the micrometeorite, they sediment at the bottom of the hole. So they collect a lot of micrometeorites with this. And with this study from Taylor et al., and also we've duplicated this study on our collection, you can see that the number of micrometeorites you get in log units is related to the diameter of your micrometeorite, and with the slope that is about -5. So the number of micrometeorites decreased very rapidly with diameter. So in that South Pole collection, they got only 1 micrometeorite that was near 1 millimeter size, but they got 1,000 that was just above 100 micrometer. And so we just pointed out that in the South Pole collection, they got only 136 particles above 400 micron. And in our collection from Antarctica, we get thousands of this large size. So how do we collect micrometeorites? We go on top of mountains in Antarctica, like this mountain or this one. You see they are very flat because they have been covered by the ice at one point. You see the ice sphere, so it looks like the ice sheet was there yesterday. But when we get some granite sample here and make the exposure dating with barium-10, we can demonstrate that this surface has been seeing the sun, so exposed to the air for nearly 1 million years here, and nearly 2-3 million years here. So all material that comes from the sky just accumulates on the surface, and if you sample the sand that you get in the fracture of the granites, you get a lot of micrometeorites. So this is me, if you want to see a picture of me collecting those sand on the mountain. And of course we got a lot of sand, and then we do magnetic extraction. We extract the magnetic grains from those sands because essentially most of the micrometeorites are magnetic and the quartz grain are not. So we get a concentration for this. So we did a lot of study on this material, and I think I will skip all the results. And just a few images of those micrometeorites. So most of them are spherules because they have been melted. When they enter the atmosphere, there is a strong heating, as said by your colleague. So the material is flash heated. It's a droplet of liquid, and then it freezes just a few seconds after. And so you have some of them are glassy, some of them have microcrystalline, and some of them, like this one, it's a monocrystal of olivine, in fact, because it's very rapid crystallization. And the ones from Antarctica, of course, the exterior part has a weathering surface, so it's not always very nice. And also you have bubbles in it because you have gas or sulfur that make holes in the material and during escaping. So not all of them are like droplets. Some are bumpy because this is the crystallization of the olivine. And you see those white spots? It's magnetite, because it's the iron in meteoritic material. When it gets heated in the atmosphere, it oxidizes in magnetite. So that's why most of these materials are magnetic. It's because of the oxidation of iron at high temperature in the atmosphere. There are rare type of micrometeorite that is made only of iron nickel oxide. So if you have a metal grain entering in the atmosphere, it melts, there is no silicate, only iron nickel oxide. It makes very nice material like this one, very rounded, and it's very resistant. It doesn't weather on the earth like olivine or glass. So sometimes you find this one, they remains, while the other type of micrometeorites have been dissolved. And this picture is very bad because it was a grain with metal. There was still metal in it and a shell of oxide, and then it rusted in the Antarctic soil, so it just swelled. You see, it looks like an old piece of metal that has just swelled and is completely rusted. So just a few polished section of micrometeorites. So there is a lot of variety of them, a lot of fun to study them. And some of them, like these ones, are unmelted. The melted ones, they are the droplets. And then the unmelted, you still see the fine-grained material of the meteorite-like. This is from a carbonaceous chondrite. And sometimes they are scoriaceous, so it's partly melted. So a lot of things to study on this material. And finally, just to show you, sometimes we make unexpected discovery. While looking for those micrometeorites in the sand of Antarctica, some of them, they are just nice sphere, very shiny and made only of glass. And some of them, we analyzed them and we realized they were not micrometeorites, they were what we call tektites. So it's a terrestrial glass that has been projected by an impact. And so we were collecting them here, and we have demonstrated that they are from this well-known Australasian tektite field that is known in Australia and Indonesia, in the ocean. But it was never observed that this projection of ejected glass was found to such distance. So we have extended the strong field of the tektite, the Australasian tektite field, toward Antarctica. And this occurred 0.8 million years ago, this impact. So to finish, just to introduce the use of micrometeorite and also meteorite collection to understand the history of deserts, because we do this job not only to understand the solar system, but also to understand the collection surface, to understand the climate of the desert, the history of the desert. So the idea is, if you collect over 1 square meter the sand and count the number of micrometeorites you find in it, the flux of micrometeorites on Earth is very well known. I told you, we know one micrometeorite per square meter per year, and so we can, if we count the number of micrometeorites, we could date the surface. That's the idea. And so we did this in Antarctica, in Atacama, in Tunisia, and it would be interesting to do this in Iran. And so just to finish, a plot that we made of the age of the surface, of the desertic surface. We studied if you collect quartz pebble on the surface and do cosmogenic nuclide measurements like barium-10, you can know since when the pebble was at the surface, was seeing the sun, in fact, and the galactic cosmic ray. And so we have example from Tunisia. We got an age of 3.3 million years of exposure. In Chile, we get ages from 1 to 6 million years. In Antarctica, it's more around 1 million years. And this is the number of iron cosmic spherules above 200 micrometers per square meter. And you see, of course, there is some dispersion. It's not so easy to measure this, but there is a tendency of correlation between the age of the surface as determined by barium-10 and the age of the surface as determined by the number of micrometeorites. So the idea, if we could do this in Iran and see if we have less micrometeorite than in Tunisia, it will tell us it will be hard to find a lot of meteorites in Iran. If we found values like in Atacama, it would be good because we know we will find a lot of meteorites. And that's how we, in fact, the place in Atacama that Jérôme will present to you this afternoon, we found this place thanks to these measurements. We first did the measurement of the micrometeorite and we said, yeah, it looks, we want to study this place further because there's a lot of micrometeorite, and then we discovered there was a lot of meteorite. So that's the interest of this. So thanks for your attention. Yeah, this is the meteorite we found by helicopter. So the idea, it was the only black stone on the surface, so that's why we spotted it by helicopter. But most of the time we travel with those snowmobiles, and if you want to see me again, it's me. So magnetic susceptibility depends on the amount of metal you have initially, so the type of meteorite, and then for a given type of meteorite, with time on the Earth, the metal rusts. So if you have you diminish the amount of metal, the magnetic susceptibility will decrease. So sometimes we use magnetic susceptibility if we know the type of the meteorite by microprobe, for example. We can use magnetic susceptibility to estimate since when the meteorite arrived on Earth. But of course, it depends on the desert. So that's one thing we want to understand in Iran is how the meteorite weathered, how fast the metal disappeared, and what does it tell us about the climate, the humidity, the temperature cycle in the year, etc. So here the meteorite will be used as a climatic probe.
So also depends on the temperature of the surroundings.
Yes, of course. For example, in Antarctica, the meteorite they rust also. But they rust at average temperature of below zero. Most of the time they are at minus 40, etc. A few days in the year there is enough sun, because the meteorite is black, to melt the ice around the meteorite, so there is small humidity, but just for a few days every year, few days, and of course the temperature is zero, so the kinetics is slow, but they rust also. So of course, if you have 60 Celsius degrees, like in Lut, the kinetics will go faster.
Thank you very much for your presentation. I'm very curious to know that are they radioactive as well as magnetic? I mean, can we detect them with an ordinary radiation detector? Any kind of radiation, alpha, beta, or gamma?
Yeah, some people they get afraid about the radioactivity of meteorite because they read new scientific news that we measured the radioactivity of the meteorite and inferred that it was this and that. But you need very sensitive detector to measure the radioactivity of meteorite. It's of course it's absolutely harmless, but it's true that if a meteorite just fell on Earth, you can have short period elements that are still in there because they were formed by the interaction with the cosmic ray in space, and they don't form on the surface of Earth. So I don't have example like cesium-137. You can measure the activity of cesium in the meteorite. If there is still activity, you know the meteorite just arrived. It cannot, it must be less than 1 century, for example. But the activity is very low. It's you need to go in a big lead volume to avoid noise, etc. So you can measure it, but it's not a huge radioactivity, of course. And for example, uranium and thorium, they are very low in meteorites compared to granite.
Can I ask a question? What could a lot of us who go to the mountains or to the deserts do to find the help and locate this? Because obviously these sort of expeditions you can, it's expensive to use, time consuming, it's difficult, but for natives it may be much easier.
Yeah.
What sort of suggestion you have, or what sort of ideas you may go to tell us where and how we can collect these and keep it for you for further research?
So the best is teaching. That's also why it's important to make such conference in various university. Like we got the meteorite, the World Meteorite Meeting this year was in Morocco, and we have been teaching Moroccan students but mostly you need to see rocks, because it looks easy, black rounded rock, but when you go in the field here, you will find a lot of black rounded rock, and most of them won't be meteorites. So you need to exercise your eyes. So the best is to have sample and to compare. And when you learn to recognize rocks in practical classes here, you have to do practical classes of meteorite recognition. A lot of people from Sahara, also from France, they bring us sample and they tell us, I think I found a meteorite. And mostly they are not, because people, they get attracted by samples that are shiny and well-rounded and not usual. Beautiful sample, in fact. And usually meteorites are not beautiful. They look like rust, and so they are not shiny, they have no specific shape. So a lot of people, they don't collect the right material. You have to see examples to understand what you have to collect. And then, of course, there are surfaces that are more or less favorable. You need to look for old surface, Because if you go to a place where the river has flooded the place and bring material 100 years ago, you won't find meteorites. You need to go to surface with the oldest possible age. So you need to have understanding of the geomorphology of the area.
I think we would be able to invite you further and ask you to prolong the speeches so that we can have a basis of this knowledge.
Yeah, and I think in the next mission we could bring samples. Also, there are already meteorite samples from Iran, but we can bring other samples from Sahara, from Atacama, and just to show them, compare them with basalt. And because, of course, when you go to an outcrop, of course, we bring students to nice outcrop along the road cut in quarries. There, the terrestrial rocks, they are very easy to recognize. But basaltic pebble that has stand hundreds of thousand years at the surface of the desert, it looks strange. It may have people think there is a fusion crust. In fact, it's just the weathering of the surface of the pebble. And so you have to get used also to recognize terrestrial rocks, but what you found at the surface of the desert. It's not like the one you have in the collection of the university.
Because you are not a physicist, or I don't know, it's a good question from your novel. I want to ask you, have you even heard about the relationship between the magnetic monopoles, which are predicted by the theory and not reasonable by into the matter? Have you ever heard any relationship between the study of the theories and the magnetic monopoles around?
There has been a search. Yeah, this idea of magnetic monopole, the existence of magnetic monopoles is debated, and people think they interact very little with matter, but they may be trapped in rocks. And so I have a colleague that tried to look for monopoles